Hello everybody. In this video we're gonna start the fifth chapter in this course, which is gonna be talking about the basic chemical calculations. In this chapter we're gonna focus on the basic concepts of the chemical calculations that are gonna be very common in our practices in chemical engineering, not only in organic chemistry. And we are gonna start with basic properties of gases, and we're gonna talk about this in more details. And this will lead us to talking about the system of units and what kind of units systems that we have and how we do the conversions. And it's pretty important actually because it's something that we deal with continuously in our applications. And then we're gonna go to the liquids and the properties of liquids and solutions, and finally we're gonna talk about the basic chemical calculations. And by this, we mean the calculations related to the chemical reactions. And this is something we're gonna discuss in the next few videos. So let's start about the basic properties of gases. And here we'll talk about the equations of state. We'll understand what we mean by equation of state and why we have this equation of state for gases and not for other phases. We'll talk about the mole fractions of gases and the properties of mixtures and the density of gases and the Dalton's law of partial pressures. These three are related or more related to the mixture of gases, not for pure gases. So let's start about the equation of states, and these are the equations that relate the pressure, temperature, and volume of gases together. So you have a relation that lets you predict how the pressure will affect the temperature and volume, or how the temperature and pressure will affect the volume, and whatever. And there are many kinds of equation, and this is the simplest form, which is the ideal gas law, which is something we're going to talk about in few minutes. But before we talk about it, there is a question or a point that I want to make clear, which is why do we have an equation of states for gases? There are for liquids, of course, but the main focus of the equation of states is for liquids. I mean for gases. And the reason we have these equations for gases is um, uh, the effect of temperature, pressure, and volume on the gas is very big. The gases are compressible materials, and these compressible materials are affected greatly with the pressure and the temperature. So if you change the pressure a lot, the gas can be compressed and the volume will shrink. The temperature might increase. And this is going to be a big change in volume and a big change in temperature due to this pressure that you applied on gas. In case of liquids, you can apply pressure on the liquid, but the pressure will not change a lot, or might be a very small change in the volume, and the same for the temperature. And also for solids, the effect is not big. For instance, if you check the effect of, for instance, the temperature on the density of a gas and the effect of temperature on the density of a liquid, you'll find a huge difference. The gas the density of the gas will change a lot with the temperature, but for the liquid, it's not gonna be that much change. There is a change, of course, but it's not as big, and that's why the gases or the gas is a phase that we need to understand how it behaves and to predict how it will behave in case of the change of the external properties or the external influences on it. There are many equations of states, and we will talk about the like some things of the equations and how they differ and why we have different shapes or types of the equations. But first, we need to understand what is this simple equation, because it gives us an understanding on how the factors affect each other. And we need to take a closer look on each one of these factors and understand more about the units and the calculations. So the equation is P multiplied by V equals M multiplied by R multiplied by T. P is the pressure. It can be in units of atmosphere, in bar, in millimeter mercury, in Pascal, in PSI. The V is the volume. It can be in meter cubed, in liter, in milliliter, in foot cube. N is the number of moles, could be in gram mole or in pound mole. R is the universal gas constant, and T is the temperature, can be in units of Celsius, Kelvin, Fahrenheit, and Rankine. Before we move to the next point, there is something that we need to keep in mind, is that we have many units for each one of these parameters. And these units belong to different systems of units, and we need to make sure that when we use the units, that we use the right unit in this equation. So we don't use a unit that is not consistent with the other units in the equation. And this is a very common mistake that causes always errors in the calculations. Um, so we need to make sure that we understand the units well, and we understand what kind of unit that we need to use in any case that we are dealing with. There are two, like the most famous system of units are the standard international unit system, which is SI units. And it's kind of well-known unit system. It's for instance, we deal with or use meter, which is split into 10 decimeters or 100 centimeters or 1,000 millimeters. Um, and the kilometer is 1,000 meter. Of course, it's kind of a well-known thing. The temperature is in Kelvin, which is, or Celsius. We have two units. You add 273 to the Celsius to be in Kelvin. The ton is 1,000 kilogram. The kilogram is 1,000 grams, and gram is 1,000 milligrams. The pressure is in atmosphere, which is 1.013 times 10 power 5 Pascal. A bar is 10 power 5 Pascal, and the atmosphere is 760 millimeters mercury. So these conversions are kind of well-known conversions. In high school, we went through all these units. Um, and this is simple. You can see that this is just multiples of tens. It's 10 decimeter, 100 centimeter, 1,000 kilogram, 1,000 gram. Of course, this is not the case here. But for the other unit, which is called the British unit, it might not be like commonly used by students in the first year until now. But in these units, you'd find that we use the foot and the inch for distance, and the foot equals 12 inches. The mile is 5,280 feet. The mass is in pound, which is lb, which is 16 ounces. The Rankine is Fahrenheit plus 460, and the pressure is in psi, which is pound per square inch. The first impression that you take about the British units is that the conversions are not as simple as in the SI units. You have the conversion factor is 12 here, and it's 16 here, and it's 5,280. It's not 5,000, not 500 anything. It's not a simple number to memorize and to know. Um, then the worst part is the conversion from British to SI units. So all the conversions here contain decimals, and or numbers that are not simple numbers. They're not easy to memorize and or to remember. So for instance, inch is 2.54 centimeter. It's not 2.5, it's 2.54. The foot is 30.48. It's not 30.5, it's 30.48. The mile is 1,609 meters. Why 9? I don't know, but it could be 1,600 only, but you have to add something difficult here. The pound is 453.6. It's not 500, not 45 or 450. It's 453.6. The ounce is 228.35. The Fahrenheit is 1.8 Celsius plus 32. The atmosphere is 414.7. It's not 15, it's 14.7 psi. Unfortunately, the British unit is used a lot in some applications, especially those related to the piping and the choice of the pipe dimensions and stuff like that. So it's common to know or to read or hear that the pipe is 3/4 of an inch or 1.5 inches, and there are some standard dimensions for the pipes, and they are all in British units. So the conversions of inch and foot and pounds and Fahrenheit and atmosphere or psi is a very common conversion that in chemical engineering applications, they're commonly used, and it's important for those who work with or are chemical engineers to know this, or to memorize them. By practice or by the common use of them, you would get familiar and memorize them. So it's something that you get by experience. Anyways, the last thing here, one last thing. The British unit is called British, but it's not used in Britain anymore or in England anymore. It's used in United States. And in the United States, you'd see that the conversion of inch to foot is 12, and this is kind of nice plot here. You can see that this is how you convert the units. So to convert from inch to foot, it is the factor of 12. Ounce to pound is 16, feet to yard is 3, and yard to mile is 1760. So it's not a uniform conversion. While here in meters to millimeters, or from meters to kilometers, grams to kilogram to ton, the factor is the same. Also for temperature, the Fahrenheit scale is very weird scale. In Celsius, you know that it's from 0, which is the freezing point of water, to 100, which is the boiling point of water. So it makes sense, you have a feeling of the number. But in Fahrenheit, starts the water freezes at 32 and boils at 212, which is very weird and very illogical thing. And the only explanation to this was, I don't know, I heard this explanation, I don't know how right or wrong is it, but it is the only explanation that I heard, is that in this scale, 37 degrees Celsius corresponds to 100 Fahrenheit, which is the normal body temperature. So if somebody is sick, his temperature will be above 100. So the 100 is kind of a simple number to memorize. If you want to know if a person is sick or not, his temperature will not or be higher than 100, so you can know if he is sick or not. um, I don't know if this is the right reason or not, but this is how it works. And if you visit the United States, you can see people saying that the temperature today is 80, and if you're used to the Celsius scale, you get scared. 80 will burn at 80 Celsius, but actually it's 80 Fahrenheit, which is kind of close to 20s in Celsius. Also, they use this way of writing the date. It's month, then day, then year. So they don't say today is April. They say today is April 15th, not 15th of April. It's not like everybody else in the world. So they have their kind of scale of unit system, which is not the same as anybody else. Anyways. So now we talked about the pressure, the temperature, the units, and all these things. We need to talk about the universal gas constant. If you remember, I kept the R. I didn't talk about the R because I wanted to talk about it in more details. Just to keep in mind that R is, or the universal gas constant, is a constant. It is a constant. So the constant has a constant value. But it is like if you say I have a distance of 1 kilometers, it's exactly like saying that I have a distance of 1,000 meters. So 1 kilometer is the same as 1,000 meters, but it's just a change of unit changes the number. So the same here, the universal gas constant is a constant, but its value changes according to the units that you use. So it's important to know the units, and the number corresponding to the units that you're using. So you can find that R equals 8.314, which is joule per mole Kelvin, or Pascal per meter cube per gram mole Kelvin. And the unit, you would notice that the unit should be unit of pressure multiplied by volume divided by moles divided by temperature, because it's PV equals nRT. So this is how the unit should be. So this is one unit. So if I use this value of R, then I have to put the pressure in Pascal, the volume in meter cube, the N in gram moles, and the temperature in Kelvin. The same for this, it's the same, but instead of it's 0.082, instead of Pascal it's liter, atmosphere, instead of meter cube it's liter. There is the unit of 1.987, which is calorie per mole Kelvin, and 10.73 in British units in psi foot cube by pound mole Rankine. So this is important to know, and this kind of is the thing that adjusts the units of the equation. So once you put the value of r, you should know which values of the other parameters or the units of other parameters to use. Of course, there might be other values of r if you have other kind or types of units here. If you use, for instance, psi with meter cube and pound mole, it's gonna give you some other value of r, which should be consistent with this unit that you're using. And now let's go to the last parameter, which is n, which is the number of moles. The number of moles equals mass divided by the molecular weight or the atomic weight of the gas that you're calculating. We'll do the calculations on. And finally, if you want to calculate the density, which is the mass by volume, you can substitute with mass divided by molecular weight instead of n, and you can calculate the density as mass divided by volume, which is gonna be PV over RT or PM over RT, and this is how you can calculate the density of a gas if you know the pressure, the temperature, and the molecular weight. So this is all for this video. The next video we're going to talk about the mixtures and how we do the calculations for a mixture of gases. So I'll stop here and we'll continue in the next video inshallah. Goodbye.